Hello. Today we'll be discussing a differential equation problem. We'll be focusing on a word problem today. Okay. 1,000-gallon holding tank. So there's a tank with a capacity of 1,000 gallons. Initially has 800 gallons of water. So initially this container has 800 gallons of water. And this 800 gallons of water has 2 ounces of pollution dissolved in it. So let's say this is the 2 ounces of pollution dissolved in it. Now, polluted water flowing into the tank at a rate of 3 gallons per minute and contains 5 ounces per gallon of pollution in it. Now, we'll say that there's a tap or any water reservoir which is actually putting the polluted water inside the container. Let's say it's going inside the container, and it is going at a rate of 3 gallons per minute. And now the solution entering the water has a concentration of 5 ounces per gallon. Now we're also told that the solution is leaving the tanker at the same rate. So it's flowing out at the same rate of 3 gallons per minute. Now we're asked to determine the amount of pollution in the tank at any given time. Now we are given the rate at which the water or the polluted water is coming in. We're also given the concentration of the pollution in the polluted water, and we're given at which rate when the solution is dissolved in the already present solution is then going out, which is 3 gallons per minute. So now we can form a differential equation. We can say dq dt, where q is the amount of pollution in the tank or in the water, is equivalent to rate n. Rate n, we're finding the rate at which the ounces are changing with minute. So we can just multiply the rate n with the concentration for the rate n, which is 3 times 5. And then we're going to subtract it by the rate out. We don't know at what's the concentration of the water which is actually leaving the tank. What we do know is that we are letting q as a variable representing the amount of particle inside the container. So we can say that we can find the concentration by just dividing the amount of solution, amounts of pollution in the solution by the volume of the solution. Now see, the volume entering the water is the same as volume leaving the water, so there won't be any changes in the volume at any given point of time, so we can just write 800. Now this is the concentration, and the concentration is then multiplied by the rate at which it is leaving, which is 3. Now if we multiply it, it's going to turn into dq dt is equivalent to 15 minus 3q over 800. Now let's not complicate things, and let's take out all of the constants which are with regards to q. So I will need some space. This is good space. So we can say that dq dt is equivalent to, now 3, we can take out 3 over 800, so we're only left with q, so it'll be easier to actually find the differential equation. Now 15 is divided by 3, which that means that 5 remains. Then that 5 is multiplied by 800, which means it's 4000 minus q. Now we don't have to actually isolate any more terms, so we can just cross multiply. So we can say that dq over 4000 minus q is equivalent to 3 over 800 dt. Now we don't have any of the dependent variables or the independent variables in any of these equations or any of these functions, so then we can just find the integral of this. So the integral of that will turn into negative natural log of 400 minus q is equivalent to 3 over 800 plus c, and this is multiplied by t, constant as a the constant. And then we can just find the exponents of each term. Let's first erase this and put this here. So now we can just say, we can take the exponential from the both sides, and we'll be left with 400 minus q 1 over c is equivalent to e raised to 3 over 800 t plus c. Now this is inverse, so we're going to find the inverse of that. 4,000, I'm sorry, it's 4,000. 4,000 minus q is equivalent to e raised to negative 3 over 800 minus c. So now we can just find the integral now. So now it'll turn into actually make it equal. Let q be the equal part, so we can say that q is equal to 4,000 minus, we're going to let this c be a multiple of e raised to negative 3 over 800t, so we can say negative c e raised to negative 3 over 800t. And now if you look back in the equation, we're given that initially it has 2 ounces of pollution already present, so we can find the value of c by just substituting t with 0. So we can say 2, this is the amount of pollution already present in the container, is equivalent to 4,000 minus c. Now if we multiply t by 0, it's going to turn to 0, and any number or function raised to 0 is 1, so c times 1 is c. So c is equivalent to 3,998. And now we find the value of c, and here, this is the amount of solution present at any given moment of time in the question above. Now have let's try to have a more graphical approach to it. Let's draw. Let's not draw. Let's generate a direction field. Here we go. What we're given is 15 ounces per minute. It's entering, subtracted by 3. We're gonna let Q be Y just because we don't have a variable Q here. Y divided by 800. That's the initial value. And if we do that, and this is the direction field that we come up with. Now, if you want to find a solution, we can use our uh, initial condition, that is when t is 0, y or q is 2. So when t is 0, y or q is right around here. So this slope, this uh, graph represents the equation, represents the final sum. Oh no, not the final sum, the final equation, which actually determines the amount of the solution in the tank at any given moment of time.
Aside from the given and shown methods in solving this problem, we can also use the integration factor or method in solving this problem. So first, after we have used the formula for concentration of solution, we know that dq over dt is equals to 15 minus 3q over 800. Now we can use this by in this next process shown below. We know that we can move the negative 3q on the left side, which makes it positive 3q, and multiply 15 times 800, which makes it 12,000. Now this becomes our IVP, or initial value problem. Now after that we will use this formula. What is this formula? This formula is the integrating factor formula. Now here is as it is written in the formula is y is equals to integration of mu of t times g of t in the d of t plus c, which is constant, over mu of t. Now, how do we get this mu of t? We get this mu of t from the coefficient in the 3q, which is 3. So, in the mu of t is always expressed to e raised to the constant, or 3 dt. Now, after it is integrated, it now becomes e raised to 3t. How about this g of t? Where do we get this g of t from? This g of t comes from the 12,000, which is in the other side of the equation. Now, after we have identified the mu of t and the g of t, we will now place this in the equation. Now, the equation becomes like this. Now, the mu of t, which is e raised to 3t, and the g of t is 12,000 dt plus c. Now, since the integrate e raised to 3t, it now becomes 1/3 over 3 e raised to 3t, which we can multiply the 12,000 in the 1/3, which makes it 4,000 e raised to 3t plus c over e raised to 3t. Did you know that you can cancel out the e3 in this side, even if there is a operation beside it, by separating these two variables? So as we separate it, e3 goes here, and while the e3 minus the e raised to 3t over e raised to 3t is cancelled in the 4000, which makes it a full number, and while the c becomes plus c over e raised to 3t. Now, how do we find the value for c? We find the value for c by applying initial conditions. While the y sub y of t is equals to 2, y of t becomes 0 where t is equals to 0. Why did we use 2? As it is stated in the given, with the ounces of pollution dissolved in it. So we are finding the amount of pollution or pollutants or similar to that in the problem at any time t. Now, as we find it, we now know that Ry is equals to 2, and while our y of t is equals to 0, so becomes the e raised to 3t in our previous, in our created equation. I mean this part. Sorry for the hint. Now, as we know that e raised to 0 is 1, it becomes 4000 plus c equals to 2. Moving the 4000 in the left side, we now know that c is equals to negative 3998. Now, uh, placing the value of c in the equation, we now know that our equation in finding the amount of pollution at any time t is y is equals to 4000 minus 3998 over e raised to 3t. So this becomes our solution in finding the pollution at any time t. Now, there are still many ways in solving this problem, and we have shown you some of the easier and more uh, faster methods of solving this equation. We hope that you can use this in the future.